Hi, I'm Nick from the Emacs Science Support Team, back with another demo of one of the tools we host. Today I will walk you through a tutorial notebook of BEM, Beyond the Exoplanet Mass-Radius Relationship with Random Forest. BEM is a Python tool which predicts the radius of an exoplanet based off several planetary and stellar parameters, using a random forest machine learning algorithm. This random forest model was trained using a dataset of exoplanets with no masses and radii, and is able to predict radii of larger planets more accurately than other methods. Installing BEM is simple. Just use pip install in your terminal like you would with any other Python packages. However, it's important that you have the correct version of Python and scikit-learn installed. Your Python version must be 3.6.9, and your scikit-learn version must be 0.20.3. If you're using Anaconda, I would recommend creating a new environment with these software versions installed. With everything installed, we can begin walking through the BEM tutorial. BEM provides a sample dataset of 509 planets with several planetary and associated stellar properties, which you can view when you load the dataset via bem.loadDataset. This function also prints out the header of the data frame. Plot dataset is a simple way to visualize the radius versus mass and equilibrium temperature of the planets in this dataset. Once the data is loaded, you can proceed to call the pre-trained random forest model. BEM's random forest regression function does this and then prints out some evaluation statistics associated with the model, including the R-square score for the test set, root mean square errors for the training and test sets, and relative feature importances. You can then use this model to predict the radius of a planet with any given value for each of the features in the training data set using the predict radius function. The predicted radius is printed out alongside the inputted values. You can choose to input just the values for each parameter or the values alongside their respective errors, with the format to do so specified in these comments. BEM also comes with another dataset that includes these error bars on each of the input parameters. This code cell shows how you can incorporate these into the random forest model using the computing error bars function. We also plot the predicted versus true radii to help assess the accuracy of this model. A third dataset is included with BEM, which is comprised of radial velocity data. Here, we use the model that was previously loaded to predict the radii of planets in this dataset. We can then plot out the predicted radii values along with their associated mass and equilibrium temperatures of each planet. Lastly, BEM includes several more ways to visualize the performance of the random forest model. Here, we plot out the training and cross-validation scores as a function of the number of training data points, the maximum number of features, number of estimators in the random forest, and the maximum depth of each tree in the random forest. These plots are all very useful for deciding how to build the random forest model. BEM also includes further ways to interpret the model using a project from another group called LIME, which stands for Local Interpretable Model Agnostic Explanations. A description of what all of the values and plots mean can be found in this link, but there's a lot of useful information here for deciding and evaluating how your random forest model performs. This concludes our tutorial on BEM, an innovative way to predict exoplanet radii. Thank you for listening.